All right, welcome everybody, and thank you all for joining us for this forum and for your interest in learning more about climate change in our coastal forests and oceans of Alaska. My name is Tom Thornton, and I'm a professor here at the University of Alaska Southeast and serve as director of the Alaska Coastal Rainforest Center. ACRC is a research center and hub that seeks to link land, sea, and society through research, education, and partnerships with agencies, tribes, and other entities that share our interest in understanding and sustaining the critical social and ecological systems of the unique and magnificent coastal forests and ocean environments that comprise our portion of the North Pacific. Research on environmental change and its impacts on human communities is a major part of our portfolio. We're excited to be hosting this forum just ahead of the United Nations 26th COP, Conference of Parties in Glasgow, Scotland, which begins next week. For those of you who don't know much about the COP process, it's the UN's Global Governance Forum for addressing climate change mitigation and adaptation. So far, with limited success, despite much hope flowing from the Paris Agreement of 2015, that was COP21, in which 196 nations ambitiously declared their commitment to limit global warming to well below 2 degrees Celsius, preferably 1.5 degrees, compared to pre-industrial levels. To get there requires concerted, coordinated action and systemic transformations to decarbonize our footprint on the planet over the next decades, however. And it remains to be seen if that will happen, or if instead we will be plagued by what activist Greta Thunberg has termed blah, 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 without significant action, despite the UN Secretary General's characterization of the most recent Intergovernmental Panel on Climate Change's assessment report as, quote, a code red for humanity, unquote. To act sensibly, though, we must have a solid understanding of the problems at hand and the appropriate levels of meaningful action. This too is something we seek to address in today's forum by stressing both climate change impacts and potential solutions in our changing forests and oceans. We are delighted to be joined by our co-sponsor for this event, the British Consulate General in San Francisco, which maintains and develops relations between the United Kingdom and the US, and is represented here today by Mr. Joe White, MBE, Her Majesty's Technology Envoy to the United States and Consul General in San Francisco, whom I will invite to make opening remarks in just a moment. We are also pleased and fortunate to be joined by a distinguished group of scientists and practitioners who are working on the front lines of understanding and responding to climate change here in Alaska. Among the areas of the world most significantly affected by environmental change, not only over the past 70 years during what has become known as the Great Acceleration of global warming and the Anthropocene, that is the geologic epoch in which humans are the major driver of change in Earth's systems, but over millennia. Our moderators for this forum will be the students from UAS's undergraduate course entitled Environmental Studies 350, Interdisciplinary Perspectives on Climate Change, our own IPCC, if you will, which I am co-teaching with Professor Jason Ammanzor, also online, from our Natural Sciences Department. Students represent the future of climate change engagement and action, so it is appropriate that they have a stake in this event. What is more, we're actually taking up their class time right now, so it's doubly appropriate that they play a major role in these proceedings. They will introduce themselves and each of our speakers after Mr. White's remarks and also manage the discussion. Finally, I want to open with a land acknowledgement, recognizing that our Juneau campus at UAS sits on one of the most beautiful landscapes on the planet. Akuquan Tlingit Ani, homelands and waters of the Aku Tlingit people, Aku, or Little Lake, being the original name for Auk Lake. Words like mitigation, adaptation, resilience, and vulnerability are often used at the COP and other forums to characterize the challenges we face in confronting the complex problem of climate change. But they hardly do justice to what Indigenous peoples have had to face and adapt to over many thousands of years in this incredibly dynamic region of major floods, earthquakes, cataclysmic glacial advances and retreats, and the like. Indigenous people here have many times faced such existential environmental threats, yet adapted resiliently and continued to thrive. Even now, we may find inspiration and edification through their leadership in sustainability, restoration, and stewardship of their homelands and waters. I know that Dune Lanker, our last presenter and an Indigenous EAC leader internationally recognized for his leadership and work in this area with the Native Conservancy, will address this topic at some depth, but it will also come through in our other talks today. With that, I will turn over to Mr. Joe White, MBA, HM Technology Envoy to the United States and Consul General in San Francisco for his opening remarks. And Mr. White, on behalf of UAS and ACRC, I want to thank you and your climate attaché, Ms. Reem Youssef, for being a catalyst and a sponsor for this event. The floor is yours.
Thank you so much, Tom, and a real pleasure to be with you all today. As Tom said, I'm the British Consul General based here in San Francisco. I'm afraid this Zoom call is as close as I've got to Alaska during my tenure, which started last December. But I'm very much looking forward to getting up to visit you all, hopefully in the new year. I hear the Diderot is quite something to behold, so that may be a good excuse to pop up and see you. But certainly the work that you're doing there and the work that we're all collectively addressing on the global climate agenda is of huge importance, and so we're very pleased to be co-hosting this with you today and very grateful for the work that you're doing generally. We're reaching a turning point in the planet, as you all know, and as we recover from COVID-19, it's critical that we build back both a greener and fairer, more resilient global economy. The decisions we make now will impact our ability to safeguard the environment for future generations. And as you know, in just a few days, global leaders from around the world will meet in the UK at COP26 to discuss some of these challenges. Biodiversity loss is an increasing crisis within this, which is undeniably linked to climate change. Any reversal will require global action on a global stage, and we'll want international partners to drive the way we use land and oceans to put nature back on a path to sustainability by 2030, certainly. Nature-based solutions can actually provide up to a third of global mitigations required by 2030, but currently only benefit from a tiny proportion, 3% of the international climate finance. And we must increase the public and private investment into these nature-based solutions so that we can meet these climate goals agreed in Paris and tackle diversity loss and improve livelihoods. Despite all this, deforestation is still occurring at a rate of 1 football pitch every 2 seconds. Now, I'm not sure whether this is an American football pitch or a British football pitch, but I'm sure in this case, it doesn't really matter. It's an appalling amount of deforestation, which is still happening as we speak. And so every country can play a part in reversing this, and we need this global action to do that. And therefore, I'm hopeful that the COP arrangements will provide a forum for our leaders to come together and discuss these things. We also need to promote sustainable and climate-resistant agriculture practices that regenerate ecosystems instead of destroying them. We must drive forward the protection of marine ecosystems and improve the ocean's resilience and to support the restoration of critical habitats, such as coral reefs, mangroves, and seagrass beds. At stake is a $4.5 trillion prize, which is rapidly opening up for governments, farmers, and businesses, which is really the value of this green economy, particularly in biodiversity areas, and the huge opportunities for market growth in healthier, more sustainable food. There is a shifting of consumer and demographic habits to want this, and this is a real opportunity for us and our communities to benefit from it. We must capitalize on this and drive a just rural transition for all people across the globe. And we do need this global action to protect and restore forests, and critical ecosystems. And that's why I'm so pleased that this conversation is happening here today and the research that you are all doing. I mean, the research community in Alaska is working on solutions-oriented science for policymakers. The International Arctic Research Center and Center for Arctic Policy Studies at the University of Alaska Fairbanks are championing the work both in the state and more broadly across the US. And the Alaska Coastal Rainforest Center, our partners on this event, is studying the North Pacific coastal temperate rainforests and the neighboring coastal ocean ecosystems. So there's a huge amount of which is going on in Alaska and across parts, particularly of my patch, the Pacific Northwest of the United States, where additionally California and Washington and others lead a lot of this climate thinking. But Alaska is a great place for this, and I think iconic in terms of people's understanding of the impact on natural and beautiful ecosystems. So having you contribute in this way is hugely exciting for us, and we're very grateful for that. So without much further ado, let me hand back to Tom, who can introduce our panel, and let's get going with the real experts and see what we can do together. Thank you so much, Tom.
Thank you very much, Joe, for your inspiring remarks. And we now move to the changing forest side of the program, beginning with a scientific overview, followed by a focus talk on climate change and salmon, and then a solutions-oriented talk on carbon forestry. We may have to hold questions between speakers in the interest of time, but we'll have a period at the end of this session for discussion. So let me now turn it over to Shailene Moeller.
Hello, everyone. My name is Shailene Moeller, and I'm a double major in English and Environmental Studies at UAS. I'm here to introduce David D'Amore and his presentation on climate change and Southern Alaskan forests. Dave is a research soil scientist with the USDA Forest Service Pacific Northwest Research Station based in Juneau, who has conducted research on the interaction of soils with vegetation and water across coastal forest ecosystems. If you have any questions during his presentation, make sure to ask them in the chat box and we will address them at the end. Please welcome Dave D'Amore.
Thanks very much for the introduction. Let me get to sharing my screen here. Get back to the start. Yeah, so, and Molly, just give me a little signal if you can't hear me well enough. But glad to be here to talk very briefly about the a little bit of the ecological natural history of forests and landscapes in Southeast Alaska and some of the impacts of climate change. First, just to ground us, we are in the coastal rainforest, and in particular in the perhumid coastal rainforest, the dark green section you see there that really is looks like it's coastal British Columbia, but of course the sliver of Southeast Alaska is in there as well. We view this ecological region as one coherent unit. This is the non-fire prone coastal temperate rainforest of the Northeast Pacific. So 15,000 years ago. Yep.
Sorry to interrupt. It looks like you're not actually present mode yet. So if you press the present, we'll see your full screen.
Let's see. Thought I had. Let's see. Let's try it again.
You might be sharing you have two screens. You might be sharing your other screen, Dave.
Okay. Yeah, let's do, okay, let me try this. Yep. Hopefully this won't backfire on me. Take it out of the docking station. All right. That might have been the problem.
It's still showing all of your slides.
Yep. Okay. How's that?
Not yet. Oh, there we go.
All right.
Got it.
All right. Sorry for that. I will. Okay. So picking up where we left off, the coastal rainforests. So 15,000 years ago, this whole region was buried under miles of glacial ice. So really, we're in a very young landscape in geologic terms, a blink of a geologic eye. So this is how the landscape looks when it first emerges from that glacial cover and kind of the parent material and the underlying fabric of our ecosystem here in Southeast Alaska. And the system has developed into some very particular units, from the angular mountains that you can still see to this day, down our hill slopes where most of our productive forest is, into our lowlands where a lot of our peatlands and wetlands exist. Looking at it from an aerial view, the landscape is a mosaic. And this mosaic goes from forested lands with above ground vegetation to peatlands. And it's actually pretty appropriate to be with our colleagues from the UK today, because one of the other places on Earth that has as extensive peatlands as Southeast Alaska is the UK. So what really is a governing factor, what controls this landscape, is the depth to water. Water, it really describes a lot. You'll see this upper left slide. Some research work I did was able to delineate the critical depth to water where you either were a wetland or not a wetland. And that was about 25 centimeters. So if that water table gets above 25 centimeters, you're a wetland. If it's below 25 centimeters, you're more likely to be upland landscapes, upland forest. Same on the lower right here, biomass. You can see the biomass indicator at the left of that red line, high biomass. The lower the depth to water, the more above ground biomass or forest you get. So we partition the landscape into these three units. These are which are defined by the depth to water: uplands, forested wetlands, and our poor fens sloping bogs. First, the upland forests, the iconic old growth forest, as it were. We don't have a lot of species. We just have about 5-6 main species in the forest. As I said, it's non-fire prone, so we get a small scale disturbance, not stand replacing disturbance like fires do. And the other end of the spectrum, our peatlands have accumulated organic matter to a depth of up to 6 meters. You can see here's we did a cross section across one of our peatlands. This is all pure organic matter, so buried carbon. I'll get to that in a minute. Upwards, and here this deposit is about 4 meters deep at its deepest. So an incredible accumulation of organic matter. So when we say Southeast forests, we're really saying Southeast ecosystems, our peatlands and our forested wetlands and the upland forest. Just a zoomed in view of that surface, very complex deposits of organic over time. So then what are the implications for what now is a pretty well documented increase in temperature, this press disturbance over time? Pretty predictable. This is from the UAF SNAP group, and just showing the seasonal pattern of temperatures. And it's very clear that we're seeing an upward progression of temperatures over the next several decades. Also, precipitation. So precipitation is a lot less predictable, but in Southeast Alaska, it's a rainforest, we get a lot of it, but we are right throughout the system, we're right at the rain snow threshold. And that has important implications for our forest. One of the most notable changes that we've been able to document is one of our trees actually is very susceptible to changing temperatures in the form of a lack of snowpack. This is the yellow cedar, a really important commercial and cultural tree in the region, has experienced a substantial decline in its population over the last century. And this is our work has shown that this is related to fine root freezing due to lack of snow to protect it. Here's a map just showing where it is on the landscape, lower slopes. You can see the red indicates where the decline is occurring. That yellow line is the modeled snow line, where you have snow protection and where you don't. You see it matches up pretty well with the decline. So one of the things that we're trying to understand too is as you have this stand replacing disturbance where you lose a lot of the above ground forest, what are the trajectories of this forest succession? Well, one is where you don't have redundant species or complementary species to replace yellow cedar, you get scrub or sometimes hemlock coming in. But where you do have the closely associated red cedar, you actually get red cedar that can occupy the same growing space. However, we're now seeing some disturbing signs. Red cedar and yellow cedar have really similar root cold tolerance. There you see on the left, the upper graph there at about -5C. And there has been some evidence of top dieback of red cedar across the landscape. So next, we can't talk about forests and the ecosystem without considering carbon. Natural systems, terrestrial systems mitigate greenhouse gases to a great extent. And so one of the things we're looking at is how much carbon we sequester in the region and where that's going to be. To put it into very accessible terms, the entire Alaska, this is not just Southeast, but all of Alaska absorbs the equivalent of about 5 million metric tons of carbon a year. So that's equivalent to about 42 cruise ships. If you buried 42 cruise ships that visit Southeast Alaska, that's in weight terms, that's the same weight. So it gives you kind of an idea of the magnitude. Where is this carbon? Most of it's below ground. This is a map of a study recently completed by colleagues that showed the distribution of the carbon below ground in the coastal rainforest, the humid coastal rainforest. Huge stocks, as I said, a lot of this is in those peatlands, but a lot of it's also in our mineral soils. Above ground, one of their key questions is, how does the carbon accretion change over time in forested stands? Especially in our reproducing stands and our young growth stands. These are some of the fastest carbon accretion rates on the landscape. This graph shows you how well stands and how quickly biomass is accumulated in these stands. And you amass up to 400 megagrams per hectare in the first 100 years. So pretty substantial carbon accumulation in these young stands. That asymptotes and the thresholds at about a background accumulation rate in the old growth forests of about 1 megagram per hectare per year. So, and finally, our carbon budget, you can't look at it just in terms of the static solid carbon. We also have a huge lateral flux of carbon, the loss of carbon as dissolved organic carbon laterally from our landscapes towards the ocean. And this just gives you an illustration of where that's occurring, fairly variable, but consistent. So the thing we're looking at, where are we going in the future? A lot of my work now is focusing on this drought-prone period. We actually go into moisture deficit in the late spring, early summer, June, July. And so what does that mean for our forests? Again, here's our 3 major landscape units. And if you look at that period, we get a period of water table drawdown. So, you know, kind of approaching more droughty conditions in the rooting zone. So what's this mean in the future? We could see this period of, yeah.
We got about 1 more minute.
Oh, sorry, we're just trying to let you know you have about, I don't know, half a minute or a minute left.
Yep. So, so we have this period where we have again, that water table, which is controlling a lot of the distribution of forests, a lot of the cycling of carbon, may dramatically change. What are the implications? Well, we'll have changing forests, as we've seen at yellow cedar. We'll have changing carbon distributions and cycling, and perhaps either increased or decreased additions to that mitigation strength in the forest. And more importantly, in this region, that whatever happens in the terrestrial landscape has an intimate connection with the coastal ocean. And again, we're going to talk a little bit about that as well, but the terrestrial and the aquatic cannot be disentangled in this region. They're intimately connected. So thanks.
Hey, hi, my name is Ezra Gray. I'm an environmental science major with a concentration in Earth systems and climate change. And I'll be welcoming Ryan Gilmore, who's going to be talking about climate change in salmon forest food webs. Ryan is a fish biologist with the Pacific Northwest Research Station and the Dune Forestry Sciences Lab. And his current research is working to understand the flows of energy that support populations of Pacific Northwest salmon and steelhead during their freshwater residence.
Thank you for the introduction, guys. Let me share my screen here really quick. Can everyone see that?
Yes.
All right. And thank you for the opportunity to present some of our research on climate change and salmon in the region. To start off, I don't think it would be a hyperbole to say that salmon are a ray of life in Southeast Alaska. Since time immemorial, salmon have supported important fisheries that have sustained the Tlingit and Haida people of the region and their culture. And today, salmon also support lucrative commercial and sport fisheries, as well as subsistence fisheries that sustain many local communities. In 2010, it was estimated that 1 in 10 jobs in the region was directly linked to the fishing industry, and 90% of rural households in the region were reported to consume locally harvested salmon. And one of the reasons this region has so many salmon is because Southeast Alaska has thousands intact watersheds where salmon spawn, where those salmon lay their eggs in gravel nests, and where many of the juvenile salmon rear before they migrate to the ocean. And as Dave alluded to, these watersheds are heterogeneous due to the topography and climate of the region. A single watershed in this region can contain a mosaic of streams fed by glacial melt, others fed by snow melt, and others fed by rainfall. But things, as Dave said, things are changing, and they're changing rapidly. By the end of 2100, there's places in Southeast Alaska that are expected to warm by up to 7 degrees Celsius. And this warming is going to have dramatic consequences on the rate of ongoing glacial recession and on the type of precipitation the region receives. In the winter, we currently hover right around freezing, but in the future, we're likely to be potentially well above freezing. And thus, we're likely to get, on average, a lot more rain and a lot less snow. And as glaciers and snowfields recede and disappear from landscapes, many watersheds are going to be hydrologically homogenized, as we say. And so instead of containing a diversity of glacial snow and rain-fed streams, over time, glacial and snow-fed contributions to these watersheds are likely to fade, transforming these once hydrologically heterogeneous watersheds into primarily rain-fed systems in many cases. And when we lose glaciers and snow-fed streams from this region, we're also losing unique physical and chemical conditions in these streams. A decade of monitoring by my colleagues, including Dave DeMore just talked, has shown that glacial snow and rain-fed streams have unique discharge regimes, unique water temperature and water turbidity regimes, as well as unique seasonal nutrient regimes in terms of carbon fluxes and nitrogen and phosphorus as well. And our research suggests that these distinct flow, temperature, and nutrient regimes support unique food webs in glacial snow and rain-fed streams that sustain juvenile salmon and trout via different consumer resource pathways, as well as at different times of the year. Specifically, what we're finding is that glacial streams have greater resources available for juvenile salmon in the spring. Rain-fed streams have greater food availability for salmon in the summer, and snow-fed streams have higher resource availability in the autumn and into the winter. And these seasonal resource asynchronies may allow juvenile fishes to move from one stream to the next, tracking peaks and valleys in resource availability as they occur through time. And if they do, or if they are able to track these resource asynchronies, our model analyses show that watersheds that contain a mosaic of glacial snow and rain-fed systems can potentially support a broader diversity of different juvenile salmon growth trajectories because of the distinct foraging conditions found across these different stream types. And importantly, in our model analyses, when we remove either the glacial or snow-fed streams from these watersheds, as we expect to happen in the future, we reduce the number of growth trajectories that the modeled population of fish can express. And importantly, we remove both the glacial and the snow-fed streams, resulting essentially in a completely rain-fed watershed. We see a very dramatic constriction of juvenile salmon growth opportunities and trajectories. So what we're seeing in these simulations is the loss of both the fastest juvenile salmon growth trajectories associated with more nomadic fish that can track these resource synchronies across space and time, and the slowest trajectories associated with stationary fishes that primarily live year-round in those colder glacial and snow-fed streams. So what these simulations, what our data and these simulations are suggesting is that disappearing cold meltwater-fed streams could result in the loss of important seasonal resource asynchronies, which could constrain juvenile salmon growth opportunities. And in turn, reduced growth opportunities could destabilize populations by reducing life history diversity of salmon that has been shown to promote salmon population stability in the face of environmental stochasticity and extreme events. And extreme events is another thing that's impacting watersheds in this region. Southeast Alaska is experiencing and predicted to experience more floods due to warmer winters and more rain on snow events, as well as atmospheric rivers. And at the same time, paradoxically, more extreme low flow events due to reduced snowpacks and summer droughts, as well as higher water temperatures associated with these warmer drought conditions. And these extreme events can definitely affect salmon. An auspicious example of this is large-scale fish spills that happen after adult spawning salmon enter fresh water. Essentially, when large numbers of salmon enter rivers and then it doesn't rain for a few weeks, the stream shrinks and salmon get concentrated in smaller and smaller areas. And at the same time, the water is generally warming. And in certain contexts, these low flows and warm temperatures can lead to salmon breathing in dissolved oxygen faster than it can be replaced by the atmosphere, creating hypoxic conditions that can result in fairly dramatic fish kills, as you can see in these pictures. But extreme flows and temperatures not only affect adult spawning salmon, they affect salmon across all of their freshwater life stages. In addition to these hypoxia events, low flows and higher temperatures during spawning can also reduce access to spawning sites and reduce the amount of suitable spawning area for salmon to deposit their eggs in. And then during egg development itself, temperature directly affects the developmental rates of those eggs and the egg mortality. And high flows during that period can scour the gravel nest where those eggs are incubating. And then during the juvenile life stage, when these fish are living in the river before they migrate to the ocean, flow and temperature can influence survival via multiple direct and indirect pathways. To understand how all these pathways influence salmon populations, we constructed a life cycle model that links population success to stream flow and water temperature. And then we parameterized it for some of the glacial snow and rain-fed systems in the region. And what we found was that salmon populations in rain-fed streams were very susceptible to higher magnitude flood events that scour the stream bed, and in particular kill incubating eggs, whereas salmon in glacial and snow-fed streams were generally unresponsive to these higher floods. Similarly, salmon in rain-fed systems are also more susceptible to summer drought conditions versus glacial and snow-fed systems. And so what will happen as floods and droughts become more frequent and severe? Well, I think these simulations and other studies as well suggest that populations in many of the rain-fed watersheds in the region are going to become more stochastic and variable through time as we see a greater prevalence of these extreme events. And at the same time, these results are suggesting that meltwater streams may provide important refuges from these extreme conditions, these droughts and floods. But again, we're losing those meltwater refuges across the region. This map highlights watersheds that currently have detectable meltwater contributions to their hydrology that may shift more to rain-dominated hydrology in the near future. And thus salmon populations in these places are likely to be more susceptible to extreme events in the future. So I think our research suggests, and research of numerous colleagues, just the capacity for streams to support salmon is going to change in the region due to the loss of meltwater streams and more frequent and severe events. However, I don't think it's all doom and gloom. There's going to be winners and losers. Some stocks may do well in future conditions, but others won't. And because of this, at the regional scale, I think salmon are likely to be okay. Southeast Alaska has a diversity of intact watersheds, a diversity of species. And those species have a diversity of life history strategies. And this diverse portfolio will help stabilize populations and fisheries at broad spatial scales. However, small subsistence communities in the region don't generally gather resources at a regional scale. Many of these communities often rely on only one or two salmon stocks and watersheds for their food security. And if these stocks fare poorly, these communities could be negatively affected. So to address this, we're working with several small Southeast Alaska communities to co-develop user-friendly modeling tools that community members and stakeholders can use to explore salmon populations could respond, to explore how salmon populations important for food security may respond to future conditions. And it's important to note that the goal here isn't to make perfect predictions. We can't predict exactly how flow and temperature regimes are going to change, let alone other important components of the system. But rather the objective is to get a better sense of the range of potential future conditions so communities and management agencies can begin preparing. And with that, I'll, I guess, take questions later on, but thank you again.
Okay, I'm Matt Schiffner. I'm pursuing a degree in Geography, Environmental Science, and Outdoor Studies here at UAS. It is my pleasure to introduce our next speaker, Caitlin Guthrie, who will be presenting on carbon forestry development in Southern Alaska and beyond. Caitlin is the Director of Forest Carbon Origination at Finite Carbon, North America's leading developer and supplier of carbon offsets. So without further ado, Caitlin, take it away.
Thank you so much. Again, my name is Caitlin Guthrie. It's an honor to be here with you today discussing solutions for a climate renaissance. As we all know, we're on a path to warming the planet by 3 to 5 degrees C by the end of the century. And turning our society around in time to keep warming below 1.5 degrees Celsius requires cutting global emissions approximately in half by 2030. And getting to net zero carbon emissions worldwide by 2050. And according to the IPCC scientists, carbon dioxide levels in the atmosphere have already dramatically surpassed safe levels. So this requires us to draw a great deal of that carbon dioxide down. We have two routes to get there. One, unproven and expensive carbon capture technologies. And two, the old-fashioned way, restoring forests and other ecosystems, including our food systems. Today, I'm going to focus on forests. Here I'm showing a graphic from a widely cited paper from Griscombe et al. From 2017, where they describe the maximum climate mitigation potential through 2030 of these old-fashioned solutions, which, as you've heard referenced earlier today, have a newfangled name, natural climate solutions. And they found that natural climate solutions can provide over a third of the cost-effective carbon dioxide mitigation needs through 2030 to keep warming below 2 degrees Celsius. And as you can see here, the vast majority of that comes from forest management. The most impactful solutions at scale globally include reforestation of degraded ecosystems, avoided forest conversion, and natural forest management, otherwise known as improved forest management. And this work has been replicated by others. It provides a robust basis for immediate global action to improve ecosystem stewardship as a major solution to climate change. Furthermore, these forestry actions also provide water filtration, flood buffering, soil health, habitat for plants and animals, and enhanced climate resilience, in addition to other co-benefits. So honing in on the United States. The United States is the largest cumulative emitter of carbon dioxide from fossil fuels of all countries in the world. And due to the immense size of US-based greenhouse gas emissions from fossil fuel use, despite this immense size, this group, Fergione et al. In 2018 found that natural climate solutions have the potential to generate the mitigation equivalent of 21% of the US's net annual emissions through 2025. So even though the US is the largest emitter, we also have high potential to offset up to 1/5 of those emissions through natural climate solutions in really the next several years and then beyond. This chart is similar to the one prior, but looking solely at the United States. And note the differences in the most impactful natural climate solutions as compared to globally. Reforestation remains at the top, and we need to start that immediately at scale. Natural forest management moves up versus globally. It's close to equal in benefit to reforestation. And natural forest management or improved forest management can look like many things. At its simplest and most effective, it consists of extending tree harvest rotation ages. Basically, we need to grow our trees older and larger. And some may say, well, this is going to give us a loss in timber supply. This would just be temporary, and it can be accounted for and replaced by things like the reforestation, thinning for fire risk reduction, as well as general thinnings and select harvest practices that will still provide timber, but continue to maintain carbon in the forest. Other practices within this improved forest management category include reduced impact logging and management that releases suppressed forest growth. As you can see, avoided conversion of forest is still important as well, specifically in high-risk areas of the country, such as the Southeast and the Pacific Northwest. With that said, many parts of the United States, including Southeast Alaska, are not at high risk of deforestation and conversion to other land uses at scale. Okay. So echoing Joe White's comments that kicked us off, I want to hone in on the finance side of things. It's been established that natural climate solutions are proven, effective, and can provide over a third of the climate change solution globally, as well as a fifth of the climate change solution in the US in the near term. And they provide us with a wealth of other benefits. To rise to this challenge, the Climate Policy Initiative calculates that we need a global annual investment of $265 billion in natural climate solutions. How close are we? Frankly, I was shocked at the mismatch. It's appalling. Currently, globally, we're only investing $14 billion annually in natural climate solutions. This is just 1/5 of our need and only 2% of the current investments that are going into climate change work. So in other words, not only are we're only merely investing 1/20th of what should be in natural climate solutions based off of the climate benefits alone, but currently we're investing 50 times what we're putting in natural climate solutions into other climate change technologies. And I find this just to be a really shocking mismatch between the potential impact and the current global financial investment focus. So this is where Finite Carbon comes in, my employer. Finite Carbon is the leading developer and supplier of forest carbon offsets in North America. We deliver the industry's highest quality financing and development services to create forest carbon projects that seamlessly align with landowner goals and management. Finite Carbon holds our projects to rigorous third-party verified standards, and we work closely with forest landowners to ensure project integrity and to maximize carbon sequestration and storage in the forest. Finite Carbon was founded in 2009, and our team includes 15 professional foresters, as well as experts from the conservation, finance, spatial engineering, and technology backgrounds. And we're all singularly focused on nature-based solutions, specifically forest carbon finance. We've supported landowners in enrolling over 3 million acres across the country in carbon management, and this has resulted in more than $750 million in unrestricted revenue. As project developer and investor, Finite Carbon covers all aspects of forest carbon development and management to scale up this solution. We assist landowners in assessing project feasibility and share information on the forest carbon process as well as current market dynamics. And from there, we design customized projects that create natural climate solutions and verified carbon credits. Each of these credits or offsets is the equivalent of 1 ton of carbon dioxide equivalent permanently stored or sequestered. So these forest carbon projects are highly compatible with current forest land use in Southeast Alaska. Listed on the screen is just a partial list of some of the land uses that can continue in the forest on land that's enrolled in a forest carbon offset project. Okay, so honing in on Southeast Alaska. The potential for forest-based natural climate solutions, specifically improved forest management in Alaska, is massive. All non-federal forest lands are eligible for enrollment in these carbon offset programs. And so in Southeast Alaska, this consists of 1 million acres, that's non-federal. That's approximately 9% of the total forest area in Southeast Alaska. And yeah, Southeast Alaska is doing incredible, honestly. About 1/3 of the eligible forest land is already enrolled in forest carbon programs. So that leaves about 670,000 acres available for carbon forestry currently. And how effective are the trees of Southeast Alaska in storing and sequestering additional carbon? You may not be surprised to hear the answer is very effective. Just for an example here, I've pulled up just the projects that Finite Carbon has worked on. We're currently managing about 750,000 acres in Alaska in carbon projects, and these projects have generated over 31 million offsets to date. And of these projects, the ones we've developed in Southeast Alaska consist of about 1/4 of the total acres enrolled in the state. However, they have sequestered about 2/3 of the total additional carbon. So Southeast Alaska is really providing an outsized contribution. And if you're familiar with the forest ecology, this is no surprise. It's due to the high forest stocking, the high growth rate in Southeast Alaska. Just the climate, the soils, the biogeological conditions are just ideal for sequestering and storing forest carbon. So to wrap up, I wanted to share with you a few examples of some of the incredible projects that we have developed in the area. For Sea Alaska, the Alaska Native Regional Corporation of Southeast Alaska, we've developed 2 projects which have facilitated Sea Alaska to transition the land from active harvest of timber to no harvest, which is incredible. And when doing so, Sea Alaska has retained the full ability to use the forest for cultural use, and it's resulting in the protection of sensitive watersheds that provide drinking water and critical salmon habitat. For Hoona Totem Corporation, whose Aboriginal ties are to the village of Hoona in Southeast Alaska, we developed and managed 1 project, which has generated about 1 million offsets and that's been transacted to date. And the revenue from these offset sales has allowed Hoona Totem to shift their focus from commercial harvest to forest protection, while continuing to create forestry-related jobs and training opportunities for members of the community. In sum, I'd say there's just incredible potential for investment in Southeast Alaska forests to build a climate renaissance. Carbon forestry in the area not only has the ability to sequester and store vast quantities of additional carbon dioxide for the benefit of all life on this planet, it protects the forest, supports Indigenous peoples' forest tenure, restores the land, improves climate resilience, maintains healthy salmon runs, and provides for the sustenance of all people of Alaska. Thank you for sharing your time with me today. If you'd like to continue the conversation or explore a forest carbon project, please reach out to me via the contact information on the screen. Thank you.
Hello, I'm Charles Thorpe. We're going to be moving into discussions. If you would post your questions in the chat. Thank you.
Tom, how much time do you want to use for the discussion? Would love to have time for discussion, but I'm also looking at the time and we're a little bit behind.
Yeah, why don't we just go ahead and take a couple now if they're fresh, and then we'll move on. But yeah, we can't do the whole 10 minutes, unfortunately. We'll have to postpone the rest till the end.
We already have 1 question for Caitlin. It's from Reem. Sorry for mispronouncing your name. Does finite carbon do work outside of the US?
We do. We recently expanded into Canada, and my colleague Dan, who is the equivalent of my role, Director of Forest Carbon Origination in Canada, is in the room today.
We have another one from Ali in the chat. I mean no offense by this, but I saw that BP is the major majority stakeholder in finite carbon. And to me, that seems like a conflict of interest. Can you speak to me the impact of that business affiliation? Caitlin?
Sure. Well, every major industry in the world needs to undergo a transition to get to net zero. And BP and the oil majors are no exception. So BP is a major shareholder of finite carbon, and their investment in us has allowed us to scale greatly. Finite carbon maintains independence, and we work with all the major buyers of carbon offsets around the world.
Thank you. Any more questions?
Well, if not, we're back on time, so we can switch over to the second half, and certainly we can come back and have additional questions on the forest side of the program. But why don't we go ahead over to the ocean side now? We're going to do a similar set of 3 talks. And so is it Zoe who's up?
Yes. Hello. So my name is Zoe Funk. I'm a natural science major with a concentration in environmental science at University of Alaska Anchorage. Since we're switching gears to changing oceans, our next speaker will be Shetty Ammanzor, who is an assistant professor at UAF College of Fisheries and Oceans. She received her doctorate in marine ecology at the Center for Scientific Research and Higher Education of Ensenada, where she worked on ecosystem engineering topics. Dr. Ammanzor has led kelp restoration projects in Baja California and selective breeding of kelp in New England prior to joining UAF. She's now focused on measuring nutrient removal by kelp farms, designing toolkits to assist kelp farmers in data collection, among other mariculture-related projects. Welcome, Dr. Ammanzor.
Thank you very much for the introduction. Let me share my screen. And yeah, it should be good to go. Yeah, once again, my name is Shetty Ammanzor. I'm a guest in the ancestral lands of the Tlingit people. Thank you very much for keeping this land so beautiful. So today I want to share with you a very short overview of what climate change is and what it means to the Gulf of Alaska. And it's actually a very nice transition coming from the previous session, because I'll be touching on some topics and moving forward with another one. So let me real quick move the speakers to my other side. The terms climate change and global warming are often used as synonyms, but they are not necessarily the same. Instead, one is a consequence of the other. Increasing global temperatures, not local or regional, but global, is the main result of an increase in concentration of greenhouse gases. Increased global temperature, both atmospheric and oceanic, are responsible for climate change, with implications that differ at a local, regional, and global scale. So with that said, climate change effects are well documented and in Alaska, very easy to perceive. Climate change represents an immediate and future threat to many aspects of life in planet Earth. But today I want us to think about the implications to food security and human settlements, as displacement of human settlements will have tremendous impact on socio-ecological dynamics. Internal displacement of human settlements in Alaska, it's a reality, and this image shows examples of 12 settlements that are exploring relocation options. Although they are not in the Gulf of Alaska, they set an example for what can be possible. Some of these displacements are related to coastal erosion, and some to flooding due to changes in rainfall patterns and ice melt. This report is a light read to learn more about the topic if you're interested. Predictions about climate change have been accurate regarding understanding what is likely to change in the ecosystem. The only negative effect about the predictions is that changes are occurring at a faster pace. So we have increased rainfall, less snow, higher temperatures, glacial meltdown, ocean acidification, and the list goes on. All of them are causing changes to terrestrial and marine systems. These systems are reducing, for example, the survival of many species. They're changing timing, for example, in spawning of some fish, increasing herbivory and predation rates in the ocean, and many other changes that are yet to be discovered. So in brief, dynamics in fish, seaweed, and invertebrates are changing. And the bottom line is that the sum of all these changes will eventually or are currently disrupting food availability, which inevitably will induce changes in our eating habits. So we must acknowledge that a rapid halt is not realistic, as this is a planetary situation. Nonetheless, passive acceptance is not an option either. Changes will continue to occur, so we must mitigate what can be mitigated and certainly adapt to new conditions. Now let's focus on Alaska. According to NOAA, temperatures in the state has increased about 1.5 Celsius since the 70s. This figure shows a timeline in temperature from 1925 to September 2021. And it is important to understand that temperature changes are not uniform over time, as shown here. Neither are they uniform in space or across seasons. So one point that I want to highlight is that global warming doesn't mean that every spot in the planet is warming or will warm. If we look at the entire state of Alaska, there's actually one section over here, close to Skagway and Haines area, that is actually cooling. Now looking at the rest of the state, both the maximum and minimum temperatures are rising. This means that summer and winter are both warmer than before, with winter warming at a faster rate. The color bar shows trends of change in Celsius per decade. So let's focus first on changes driven by an increase in atmospheric temperature. And we'll get to the ocean pretty soon. So far, we know that snow-free days have increased by 10 days, more or less, since the 70s. Glaciers are retreating, causing changes in ground and stream temperatures. And to be brief, increased stream temperatures, as one of the speakers just showed to us, is affecting timing in, for example, fish runs. Warmer temperatures are also, precipitation regions, let me start with that, in the Gulf of Alaska are also changing. In fact, in Juneau, rainfall has increased since the 70s, and this is in part because winter precipitation is falling in the form of rain rather than snow. Now, warmer temperatures are also responsible for longer growing seasons. This means periods that stay above freezing. The combination of increased precipitation and increased growing seasons lead to an increase in evaporation rates that will inevitably result in less moisture trapped in the ground. And we learn a little bit of this with Dr. D'Amore. All of this, in turn, increase the probability of fires. So leaving the atmosphere and going to the ocean, I can be brief and just mention that the Alaskan Pacific is getting warmer. Sometime in the mid-90s, the ocean started warming up, and we haven't had a cooling event ever since. As shown in this figure, heat content anomalies are growing larger towards the warmer side, and it's increasing in magnitude. This other figure shows that heat distribution in the ocean, just like in the continent, is not even. Some parts of the ocean are actually cooling. The heat content in the Gulf of Alaska, though, has rose by 1 watt per square meter since 1993. And to put this into a little bit of a more tangible example, 1 watt per square meter is the energy needed to lit a single Christmas light for 1 second. Now think that the Gulf of Alaska is actually huge, so that's a lot of lit Christmas lights. So far, we know that warming oceans are responsible for changes in the distribution of species, and we may have read that some fish species are actually migrating north, some kelps are retracting while others are taking over. Water temperatures are enhancing conditions for ocean acidification effects, which affect shellfish development and their performance. Increased ocean temperature is also responsible for sea level rise, which at the same time is related or linked to changes in estuarine dynamics. And we gotta be very careful because they can be responsible for displacement of people settlements. In general, displacement of coastal settlements are often linked to increase in frequency and intensity of storms, which in part lead coastal erosion. So you see, everything gets, it's very linked, and sometimes it's hard to tease details apart. Finally, more and more intense storms are expected to reduce the number of days for safe navigation. We could expect that this will impact transportation costs, just to mention one of the many effects that limited navigation can have in Alaska. Let's not forget, though, that natural environmental variability is normal, but the extremes in this variability are exacerbated by global warming. So let me bring you back to the beginning of this conversation. A rapid halt is not realistic, yet passive acceptance is simply not an option. So perhaps this is the best time to stop, think, and link traditional ecological knowledge with stewardship efforts with a scientific method to learn together and faster in such a way that we can adapt with a sense of equality, respectful to people and respectful to nature. So with this, I want to invite you to pay close attention to the next speakers, and I'll be happy to continue the conversation when we have time to do so. Thank you very much for the invitation to participate in this forum.
Hey, my name is Cassandra. Our next speaker is going to be John Harley, a research assistant professor with UAS at the Alaska Coastal Rainforest Center. He's going to be talking today about adapting to increased marine food security threats in Southeast Alaska.
Hey everyone, thanks for having me. Just want to thank the British Consulate and ACRC for putting this event on. I'm really looking forward to discussing things with you all, and had some great presentations so far, and hopefully I can continue that trend. So I'm going to be sharing with you some of the research questions that I'm working on as an assistant professor here at the Alaska Coastal Rainforest Center. Specifically, for the last couple of years, I've been working on HABs, which are harmful algal blooms. So let me see if I can, there we go. So what are harmful algal blooms? They're generally the proliferation of single-celled phytoplankton or cyanobacteria. So oftentimes we see them in conjunction with what people call things like the green tides or the red tides. These vast swaths of oceans or Great Lakes can turn into this very phosphorescent color here. And these blooms can actually produce toxins which are dangerous for humans and wildlife. In particular, one of the species that we are concerned with here in Alaska is a phytoplankton species called Alexandrium. And this is a dinoflagellate that actually produces a number of different toxins. And it's not particularly important what these toxins are, but they can all be pretty dangerous for humans. They are collectively known as paralytic shellfish poison or paralytic shellfish toxins. Those two terms are kind of used interchangeably. And those toxins can accumulate in filter feeding clams and mussels. So shellfish species that we all who live on coastal areas like to eat, and an important subsistence food for Native Alaskans, especially here in coastal Southeast Alaska. Alaska has had a number of cases of paralytic shellfish poisoning since 1993. And unfortunately, a number of those have been fatal. Most of the cases that we have seen of paralytic shellfish poisoning in Alaska have come from Southeast Alaska. So in particular, there was a large outbreak event in Haines in the early 2000s. There's a very large outbreak that occurred on Prince of Wales Island in the community of Metlakatla in 2011. And we unfortunately had a fatality in Dutch Harbor as recently as last year. It's not in Southeast Alaska, that's in the Aleutian Islands. But just to illustrate that paralytic shellfish poisoning is an ongoing threat to people who consume shellfish in Southeast Alaska. In response to the concerns over harmful algal blooms and the safety of traditional and subsistence resources, the Southeast Alaska Tribal Ocean Research Group was formed in 2016. It was a collaboration between 16 Alaskan Native group tribes initially in Southeast Alaska, and we've since expanded that to include other groups from coastal Alaska. And the group has been monitoring harmful algal blooms in their communities for the past 5 or 6 years. And they've collected a lot of data, and some of these data sets are pretty singular in the region in terms of their contribution to the overall scientific knowledge of harmful algal blooms. So here, for instance, is the concentrations of the paralytic shellfish poison toxin in a species called blue mussels. This is Mytilus edulis. Something that we use for monitoring efforts, both because they're consumed by people and also because they uptake and excrete the toxin very quickly. And as you can see, there's kind of a seasonal pattern to these blooms. We typically see blooms in the summertime, during the months of May to September. And then the blooms are typically pretty quiet during the cold winter months in November through February. But that pattern is not always seen. And one of the questions is, how is that pattern going to change in future climate change scenarios? What I was curious in is what was happening before 2016. We actually know for sure that there have been harmful algal blooms in hundreds of years prior to when we began our monitoring efforts, both from traditional ecological knowledge and in 1799, hundreds of captured Aleut hunters were killed in an area that's now known as Peril Strait, just north of Sitka, from eating toxic shellfish. So that was more than 300 years ago. The Cedar partners have also collected environmental data like sea surface temperature, which is shown here, and salinity data, which is a little bit more complicated in terms of a seasonal pattern. But most of these communities, this is the only longitudinal record of these pretty basic and fundamental oceanographic parameters that we have. And so this has been really, really helpful for building predictive models, which is what I worked on as a postdoc student up until a few months ago. So when we model the average concentrations of PSP, I plugged everything into some machine learning models that took into account environmental variables, some of which were being collected by the tribal partners, and some of which I gathered from state and federal agencies. And the model was pretty good at predicting the harmful algal blooms, particularly the timing of the harmful algal blooms. But this is something that can only be improved as we include more data. And specifically, the thing that I'm interested in including is data in years prior to 2016. So how do we include years of data for which we weren't measuring shellfish toxins or doing phytoplankton net flows? Well, the key to that might be in examining kind of the important drivers of harmful algal blooms. So if we look at the variable importance in my machine learning models, one of the things that stands out is sea surface temperature, or SST. That's the measurement of the skin surface temperature in these communities. We usually just take a bucket of the upper 1 meter of water and measure the temperature therein. And that's definitely a critical control on the development and formation of harmful algal blooms. So this is where the traditional knowledge of shellfish toxicity comes in. In a book featuring interviews with some Tlingit elders, some of them mentioned that that there was how they knew to stop harvesting shellfish was based on the timing of the herring spawn. So they would use that ecological event happening in order to basically signal the end of their shellfish harvesting season. And as if you can see this, the phrase that they use to describe this is the translation is plant month in the sea. And that sort of makes sense given the appearance of both harmful algal blooms and the phytoplankton algal blooms, which can often turn the water kind of a greenish or chalky white color. It certainly seems like plant month in the sea. And so based on this traditional knowledge, one of the things that we were curious about was if we could use this traditional knowledge of the timing of the herring spawn related to harmful algal blooms to our advantage. One initial question was, well, is there a lot of overlap between the communities that we're currently measuring harmful algal blooms in and where the herring are spawning and where they have spawned historically? And to work from Tom Thornton and others, we actually have a pretty good idea that the traditional herring spawn areas were even more extensive than where we currently are monitoring herring spawn. And so it's highly likely that most of these communities where we're measuring HABs and shellfish toxins have experienced or currently are experiencing herring spawn activities. So it could be a tightly linked metric in terms of the spatial association. We also have the herring spawn data from the Alaska Department of Fish and Game going back all the way to several decades. And so if we look at sort of the date of the maximum spawn, which is the timing of when those herring spawn, you can see that there's quite a bit of variability in a lot of these herring spawn runs. So sometimes the herring spawn, like in mid-April, and in other years they spawn in mid-March, and some years they spawn in mid-May. So it can vary by up to several weeks. And the question is sort of what's driving the timing of that herring spawn? And is that something that we can model using environmental variables? This is directly related to something called the silver wave hypothesis, which is the idea that the herring are spawning later at higher latitudes, which is likely because they're responding to colder water temperatures, which are typically found at the higher latitudes. So if you look at the mean spawning date for a lot of these, for a lot of the herring, you can see that in the southern area of Southeast Alaska, so Prince of Wales Island, Macala, the herring spawn usually in early April. But if you go all the way up to where in Juneau area where ACRC is located, you can see that that typical herring spawn date usually occurs later into May and occasionally even into mid-May. And so the idea is that this migration of ducks and sea lions and other marine mammals are sort of following this silver wave as you go further north, and that might be explained by the sea surface temperatures. So which environmental variables are driving the timing of the herring spawn? There's been several ideas that have been posited about this. It could be something related to the tides. They spawn during maximum tides or minimum tidal swings. The temperature has also been implicated in this idea, or the sea surface temperature, as I mentioned. I'm kind of hoping that it's the latter. If you look at the date of the herring spawn in relation to sea surface temperature, it does seem to be within a somewhat reasonable temperature range. And interestingly, it seems to usually be below 8 degrees Celsius. And that is interesting because that's kind of the window in which we start to see harmful algal blooms occurring is temperatures above 8 degrees Celsius. Specifically in the summer months, we typically see the Alexandrium and our net toes right around 10 or 12 degrees Celsius. And so it's likely that that herring spawn temperature threshold does precede the Alexandrian threshold. Of course, sea surface temperatures are forecasted to increase as a result of climate change. And so one thing that we're interested in is how is this going to change in the future? Are these things going to stay coupled or decouple? And that's part of our research questions is how are these events which are linked in time according to specific variables, how are they going to change? And can we use that to our advantage? And with that, I will, I guess, not take any questions for the moment, but we'll go on to our next speaker.
All right, thank you, John. My name is also John, John Seymour. I'm a UAS student in the environmental science program. And the speaker, the final speaker that we have here for you today is Dune Lanker. And he's the president and founder of the Native Conservancy. He is a social change activist and a renowned Native rights leader. Some of his work included helping to win the preservation of more than 1 million acres of the Copper River Delta, and has been widely recognized for that. So without further ado, take it away, Jim.
Yes, can you hear me okay?
We can.
Okay, good. I'm really happy to be with you all. I'm here in Talkeetna, Alaska, watching my 6th grade daughter basketball game. So
June, it sounds like we've lost your audio.
yes, can you hear me?
Oh, yes, we can.
Okay, what I'll do is I'll keep the video off of me and hopefully that'll give me better transmission. All right, my name is Dune Lanker. I'm an Eyak Athabasca native from the Eagle Clan here in the Copper River Delta region of Alaska. And my Eyak name is Jamutsiki, which translates into little bird that screams really loud and won't shut up. And I received my Eyak name after the Exxon Valdez oil spill happened in our backyard. I'm a lifelong fisherman and conservationist since the oil spill as well in 1989. And now I'm a kelp farmer during these climate changing times. The Native Conservancy is a small nonprofit in Cordova that was originally formed to protect our ancestral homelands in the Delta and the Prince William Sound regions. Native Conservancy eventually grew to support traditional subsistence pathways with regenerative solutions for coastal Native communities here in Alaska. The Pacific salmon are critical to our subsistence and wild salmon way of life practiced by coastal indigenous communities in Alaska for generations, the same as the coastal temperate rainforest all the way down to Santa Cruz. Our wild salmon reproduce in river and lake habitats in which glacier ice is currently receding at unprecedented rates, along with permafrost and sea ice. And the salmon are directly impacted by warming temperatures, glacial recession, and hotter water temperatures. An average return of salmon annually to the Copper River Delta is around 1 to 2 million sockeyes, which are red salmon, returning home after their 4 to 5 year world tour. In 2018, only 44,000 sockeyes came home. In 2019, the ocean heated up to 76 degrees for 3 weeks, killing literally millions of krill, mussels, wild kelp forests, salmon, and birds. Following year in 2020, only 85,000 sockeyes found their way home. By 2021, this year, over 500,000 sockeyes and 50 million pink salmon returned, but the sockeye run was less than a quarter of our annual returning salmon runs. So after witnessing this demise of our salmon firsthand, our Native Conservancy Am I back on?
Yes, you are.
Okay. After witnessing the demise of our salmon firsthand as a commercial fisherman, our Native Conservancy decided to look at global solutions and do our part and do what we can while it still matters. One of our bold strategies, besides catching traditional seafoods for our elders who are dealing with COVID, climate change, and now less salmon, was growing kelp to restore habitat, feed our people a traditional food source, and in the process, build a regenerative economy. One of our key advisors, Michael Bazanson, who started the organic food program for Whole Foods USA, said to us, if it's not regenerative, just don't do it. We love kelp. Kelp is the future. Kelp is the hemp of the sea. This multifaceted ocean solution connects us with subsistence practices of our ancestors and has great potential for habitat restoration, deep sea carbon sequestration, as kelp can sequester carbon 5 to 20 more times than carbon can in living terrestrial forests. Growing kelp is highly nutritional omega-3 sea vegetable, and it has a range of other benefits for healing our ailing planet. Other than being able to create 150 plus different food products, it can also be used to make biofuels, bioplastics, pharmaceuticals, nutraceuticals, cosmetic, and animal feed. If 2% of kelp is added to animal feed and fed cows, it can offset their daily emissions by 50 to 60%. So cows should be eating kelp. Growing kelp in Alaska also complements the commercial fish.
Sounds like Dune has dropped off again. We'll give it a minute to see if he's able to rejoin.
Back?
Yes, you are.
Okay. The growing kelp industry can offset our commercial fishing jobs because we're able to, I don't know what happened here. Can you still hear me okay?
We can, yes.
Okay. For some reason, my screen just went away here, so I don't know what's happening.
We're still seeing a magnificent bowl of kelp.
Okay,
on our
yes,
screen.
yeah, I know that's yummy stuff. But the fishing season starts in May and ends in October, and kelping is opposite, starting over mid-May. So the native people in Alaskan coastal communities have witnessed firsthand how
So he's got dropped again.
okay, I think I'm back.
Yes, go ahead.
Okay. And the family fishermen, like my family, 7 Little Indians, were struggling to retain a portion of the seafood profits to support our families and fishing way of life. We must act quickly to create a more sustainable community model for the kelp and mariculture space. So the Native Conservancy is boldly stepping up now to break down any barriers to entry for Native people and to create a pathway to relocalize lost fishing jobs and help build regenerative economies for our people, to give our Native women and youth a reason to come back to our villages. We want to help Native people and their families to confidently step back into an ocean way of life that is healing, regenerative, and hopeful. Here at the Native Conservancy, we are creating pilot programs that can be duplicated in Alaska and in coastal communities around the world. The Native Conservancy is addressing the numerous barriers to entry. There's about a dozen of them or more, including helping Native communities complete landscape and site selection analysis, how to get their ocean farms permitted, teach them how to source, harvest, and cultivate their wild seed in their own portable seed nurseries, how to secure the right boats to deploy, monitor, and harvest their ocean farms, then figure out the best approach to process, value add, and direct market their products themselves. This includes helping create a structured fund that can provide long-term, low-interest deferred loans to give them time to grow their businesses so they don't have to sell or lose their farm to get a farm in the ocean. Our Native Conservancy programs take a practical and inclusive Native-owned, Native-led approach to tackling these hurdles and challenges and creating a new, brighter future for the Native people in our oceans. We're working on the forefront of bridging our traditional subsistence and ocean lifeways in bold and innovative ways.
He may be doing this for dramatic tension, but
okay, I think I'm back. Okay,
you are.
Native-owned, Native approach to tackling these hurdles and challenges and creating a brighter future Native people in our oceans. We're working on the forefront of our traditional subsistence and ocean lifeways in bold innovative ways to ensure that we quickly and effectively address food security and food sovereignty issues on our coastal communities so that they thrive, not only for today, but for generations to come. A friend of mine, the ally of the Native Conservancy, Dr. Elizabeth, wrote an article, "How can you call yourself sovereign if you can't feed yourself?" Doesn't that just say it all? How Oh my God. Okay. Okay.
Yeah, go ahead.
All right. Last thought. So Dr. Elizabeth wrote this article. How can you call yourself sovereign if you can't feed yourself? Doesn't that just say it all? How are we as a human race going to continue to exist anywhere if we don't figure out how to heal our oceans, the air, and our land so we can continue to feed our people? Our Native Conservancy is doing everything we can to be a part of a global solution. and build a regenerative economy that helps heal our precious environment, that feeds our people traditionally healthy foods, and one that builds a truly all right. The final thought was the green race for our Mother Earth has begun. We're in, are you? And so sorry about the bad transmission here in Talkeetna.
Well, thank you, Dune, and thanks to all our speakers. We just have a few minutes left, although we can certainly go over a few minutes if people are willing to hang around. Are there, Charles, are you still monitoring? Are there other questions in the chat, or can I throw one out while you're pulling them together?
Yeah, you can throw one out. We can, one question was asked, but John Harley already got that, so very good.
Okay, well, maybe I want to attempt to bring in a number of our speakers. I mean, we've heard about forests in the ocean, kelp forests, forests on land, their importance in sequestration and as nature-based solutions. I want to ask our Forest Service friends, even though I know they're not so much on the management side, but do they see and others see a prospect for some kind of integrated action that would combine ocean and forest solutions and target maybe those areas where you could optimize nature-based solutions to protect the most critical resources like salmon, shellfish, and so forth? So it's really open to anybody, but I thought maybe I'd let our biggest landholder, the Forest Service, weigh in somewhere in there.
I'll start and then I'll let Ryan go. This is Dave. You know, interestingly enough, during the Obama administration, there was a great kerfuffle because many agencies were crossing territorial lines, as it were, you know, or administrative lines. And there was a lot of sort of concern about that, because agencies have a very specific direction, funding authority. And one of the things that actually the nexus, which is a real problematic, are anadromous salmon, because they go from Department of Commerce to, you know, Department of Agriculture. And what do you do there? And then within the state of Alaska, right? Within the streams is Alaska Fish and Game, and the terrestrial is the Forest Service. It is a challenge, especially when you have very sort of strict administrative lines, and especially funding authorities are very particular when it comes to what you can and can't do. So collaboration across those lines can be a challenge, though we, of course, in our research groups, as Ryan's illustrated and I tried to highlight, we've blurred those lines in research, and we know we have to look at it as, you know, an entire system. But still, administratively, it's difficult.
I'd love to hear from Dune and maybe from Caitlin as well about what they might like to see to kind of scale up, scale out that level of collaboration with federal state agencies.
Can you repeat the question?
Well, just thinking about ways of integrate the solutions and allow for scaling up of what we're calling nature-based solutions, so that you link the terrestrial landholders, managers with the native entities, the federal agencies like the Forest Service with the native entities like the corporations, and then same thing on the waters, those who are trying to build those nature-based solutions with the regulators and so forth. What do you think is needed on the sort of NGO private sector side? I don't know.
Okay, I'm
back. Okay. Did you get the question?
Yeah. I really apologize. The transmission must be televising the basketball games or something. But, you know, I think that we need to, the industry has to work hand in hand with government, you know, try to change the policies and the laws that can actually help do more carbon sequestration than it can. For example, like, you know, it can sequester carbon 5 to 20 more times than living terrestrial forests. Well, that's because we have to take it out of the water every spring. It'd be great if we could do carbon sinks and leave the kelp in the water year round and actually do direct seeding so we can help replace some of those kelp forests that are dying, that can't move and can't migrate quick enough. And the thing about kelp forests is that they harbor create a home for 300 to 350 different species, including salmon and herring that have yet to recover from the Exxon spill. And so what we're hoping is that, you know, we can work with government.
I seem to have lost him again.
I hope you got that.
Yeah, I think we got most of it. And maybe Caitlin, if you want to weigh in, if you're still there, from your perspective.
Sure, happy to. Yes, as I mentioned, you know, federal agencies are not eligible for the voluntary forest carbon offset programs, but that doesn't stop, you know, federal lands from managing their forests for carbon sequestration. And, you know, what's called proforestation or extending harvest rotation ages is key for the sequestration of additional forest carbon, as well as other forest management actions such as selective cuttings that leave the soil carbon intact. And as we heard earlier in this session, so much of the carbon in forests is stored in the soil. And you know, I do want to note that the municipalities, state agencies are eligible to enter the carbon market. So really, you know, all landowners can work in conjunction for this management.
Great. Okay, we probably have time for one last question, if there is one. John?
Two questions. One's directed towards Dune. Are there major impacts on the environment when more kelp is introduced? How do we keep this in balance when people begin to commodify and capitalize? Dune, you are
I think you're muted, Dune.
By law, you're only able to put kelp in 30% of a bay. So, you know, that's going to keep 7% open. And like I said, when fishing ends, that's when kelping begins. So there's not going to be major conflict between user groups. So it really, you know, all the kelp has to be out of the water by law every spring. So I think as far as impacting the environment, I think the important thing is to figure out how we can carpet the ocean with kelp as fast as we can to help with ocean acidification, to help with ocean warming, and to help with ocean rise. So I believe that industry and government have to figure out how to work together to really help make this a good, thriving industry for all the critters that make a living.
All right. Are there any other final thoughts or questions?
The second one is a question to speakers, but also their audiences from Reem as well. Given your extensive work on this and expertise, what would you like to see the nature-based solutions discussions and the negotiations at COP26 focus on? So thinking about what is happening in Alaska, but also globally. I think it's a good one to end on.
Mm-hmm. Anybody want to jump on that one?
Sure, I would I would love to see a focus on additionality of and accounting, to a key aspect of nature-based solutions is that they're measured accurately and that they're properly accounted for in the global framework, so that, say, if an action is taken in one country but offsets are purchased in another country, to ensure that they're not counted twice. And that's a really key factor to build up this market and the nature-based solutions.
Yeah, I put a comment in the chat. This is Dave Demore again. The free lunch that comes with natural systems in the United States, about 14% of greenhouse gas emissions are taken up by terrestrial ecosystems or by forested ecosystems. Well, a big question when you're negotiating greenhouse gas reductions is you're assuming that number will decline, because then you're going to have to increase. So that's a key discussion point of how much do we know about the sequestration potential of our forested systems? Will that number remain the same? Can it be increased? Will it increase, or is it going to decline? So.
Yeah, good point. All right, I think we'll have to end it there. Thanks to everyone for your presentations. Thanks to the students for your moderation. And again, thanks to the British Consulate General for your support for this event. And we hope to continue the discussion. And Reem, I see you're still on there. Do you have any advice for us to follow the COP in terms of these issues, or to stay tuned?
Well, thank you, Tom, and everybody. This has been really, really exciting, and yeah, lots to learn from what's happening in Alaska. Definitely, I think there will be some virtual aspects to COP, so please stay updated, listen to the news, see what's happening. There'll be lots and lots of announcements on nature-based solutions, but lots of other things as well. And perhaps after COP, we can reconvene and talk about the outcomes, if that's of interest to everybody. Thank you, Tom.
Yes, definitely. And thank you again for your support. And a big thank you again to everyone for participation. And we'll say so long and stay tuned. Bye-bye.